हाय गाइस, वेलकम ऑन दी चैनल। सो किसी स्टूडेंट ने मेरे से पूछा था कि डिस्प्लेसमेंट करंट क्या होती है। तो इस छोटे से लेक्चर में हम यही डिस्कस करने वाले हैं दैट व्हाट इज़ द डिस्प्लेसमेंट करंट। ओके, तो हम यूजुअल करंट का बात करते हैं। जैसे मान लो कि अपने पास में कोई वायर है ऐसे, एंड इस वायर में कोई करंट फ्लो कर रही है। तो करंट किस वजह से फ्लो करता है? बिकॉज ऑफ द मोशन ऑफ द चार्जेस। जैसे हमने कोई एक इलेक्ट्रिक फील्ड लगा दिया, मान लो हमने एक इलेक्ट्रिक फील्ड लगा दिया किसी डायरेक्शन में, इधर की तरफ, राइट। तो इलेक्ट्रॉन्स हैं वो मूव करेंगे अपोजिट टू दी इलेक्ट्रिक फील्ड, वो इधर की तरफ ड्रिफ्ट होंगे एंड उसकी वजह से एक करंट फ्लो होगा आई इधर की तरफ। तो ये अपने पास में एक जनरल करंट हो गया आई, जिसको हम बोलते हैं द रेट ऑफ फ्लो ऑफ चार्जेज। ओके, अब क्या होता है कि लेट्स सपोज एक अपने पास में कैपेसिटर है, ऑलराइट। So I'm just talking about the parallel plate capacitor, and let's suppose it is connected to a battery, and at some point we have just started this circuit. So at some point there will be some current flowing I, right? तो अगर मैं यहाँ पे देखूँ तो यहाँ पे अपने पास में लेट्स सपोज किसी पॉइंट पे आ रहा है पॉजिटिव चार्ज एंड किसी मोमेंट पे यहाँ पे आ रहा है नेगेटिव चार्ज, राइट। नाउ अगर यहाँ पे देखूँ तो करंट एक कंटिन्यूसली करंट फ्लो हो रहा है एंड आई कैन से दैट हियर in this part of the circuit there is a current because of the flow of the electrons. So electron must be going like this from this side, and then they must be going like this. Okay, so let's do the calculation of the magnetic field. Okay, why I'm doing the calculation of magnetic field? Because I just want to understand that is there any other current other than the displacement current. So let's suppose I'm taking the outside wire and I'm taking a Ampere's loop to calculate the magnetic field. So I am just taking a loop like this. Then according to the Ampere's loop, if I apply the formula, so then I will say that see, there is some current going inside it. So then I will say integration of b vector dot dl vector for the loop will be equals to mu naught I. Okay, यहाँ से b कांस्टेंट है तो b को हम बाहर निकाल सकते हैं. Then I can say b times of 2 pi r is equals to mu naught I. So the current surrounding or current going through this wire is I, and from there we get the magnetic field surrounding this wire, that is mu naught I divided by 2 pi r. So this much amount of magnetic field we get. All right. Now what I do right now, I have taken the loop like this. Okay. Now instead of taking the loop like this, I am taking the another kind of loop, which is kind of a pot, or you can think like a shape which has the opening here. This is the opening, right, and this entire surface is closed. Okay, so if I say again that the current passing through this port, so port is something like this. Okay, if I just again draw this complete diagram, so then we have this wire and this is the capacitor, right, and we have taken a port like this. So how much is the current crossing this port? We'll say 0. Okay, and then if we apply the Ampere's loop, I have taken a loop like this, and then if we apply this Ampere's loop, and again if we say, so then we'll get the integration of b vector dot dl vector for the complete loop is equals to mu naught sigma I, and where the total current crossing this port is 0. And that's why we can say b times of 2 pi r is equals to 0, and b from here we get at 0. If you look at these two results, these are giving the magnetic field of the same place, which is the across this port's surface, or from here at this place we are getting the magnetic field, and they are the contradictory results, where at some place you get from the one result you get that the magnetic field is this much, the b is equals to mu naught I divided by 2r. The other place you get that the b is equals to 0. So it is incorrect, right? So one of them must be correct, and if we bring, let's suppose, a needle at some point here, if I bring a needle over here, magnetic needle, so of course it will be deflected. From there I get that here the magnetic field is non-zero, right? Magnetic field is non-zero. It means the current must be non-zero through this port. All right, so what do we understand from here is a very important thing, is that see here there is a current which is passing like this, and now this current must also pass and should also cross through this surface of the port. This gives us the another kind of current which is coming because of not the flow of the electrons but because of some other reason. Now let's look again at this surface and let's see what is happening. So inside the capacitor at some moment we have charge, and this is a positive charge. At some moment there is a positive charge q and there is a negative charge minus q over here, right? And this charge is continuously changing. If the charge is changing, then the electric field over here, that is also changing, right? Because if you remember the electric field inside the parallel plate capacitor, that is sigma divided by epsilon naught. So because the charge is changing, so the current is also changing. I don't know what is happening this. So we have electric field which is sigma divided by epsilon naught. तो यहाँ पे चार्ज चेंज हो रहा है तो सिग्मा भी चेंज होगा, and that's why the electric field will change. And now there must be some current which is flowing because of the changing electric field. There must be some current flowing because of changing electric field, or I can say changing flux, changing electric flux. Okay, this will be very important because changing electric flux is giving rise to changing electric field, and changing electric field must be giving rise to the changing magnetic field or magnetic field. Something like this should be happening over here, because we have seen this, that a magnetic field gives rise to the electric field. In the previous chapter we have seen in this. So here also something should be happening like this. So let's see what is the flux. So according to, if we come to the Gauss law, now this is incomplete the derivation of this displacement current. So if I apply the Gauss law for electromagnetism or electrostatics, so I can say one thing, that the total flux through a enclosed surface phi is equals to q in divided by epsilon naught, right? Okay, so yeah, so let's suppose at some point of time there is some charge q on this surface of one of the surface of this capacitor's plate. Okay, so at some moment we have charge q, right? So I can say that the dq by dt is the current. So from there I can say q is equals to epsilon naught times of phi. So I can say dq by dt, the current, is equals to epsilon naught times of d phi divided by dt, right? And this is our the displacement current. The displacement current id becomes equal to epsilon naught times of d phi by dt. So this is the expression for the displacement current. And now see, this current is flowing because of the changing electric flux. All right, so let me conclude over here some things, that if I look at this capacitor again, so I can say that there is a current because of the flow of the charges, right? So there is a current because of the flow. So I can say the current because of the flow. And now there is another current which is happening inside the capacitor because of the changing flux or the changing electric field, and that is the displacement current. So this is the current flowing because of changing flux. All right, now it means if I come to this this Ampere's law, so there is a missing term in the Ampere's law. I should write it like this, that actually according to the Ampere's law, if we take a closed loop, so then the total integration of the line integration of the magnetic field along the closed loop must be equals to mu naught times of all the currents, where these currents include both the flowing current and the displacement current. So I can say it like this: mu naught whatever the I because of the charging plus I displacement. Okay, or otherwise I can also write it like this, that it is the closed integration of B vector dot dl vector is equals to mu naught I, and I displacement is epsilon naught d phi divided by dt. And this is the correct format of our this Ampere's law. This is the final format of Ampere's law. Okay, let me. All right, so this is the final format of our Ampere's law, right, where this is our displacement current. So I hope you must have understood this concept of the displacement current, and now there are the other videos available on this channel where I have covered a lot other concepts like this, which are like quite typical concept to understand in the physics, which are very important to go through. So you can just watch the other videos, you can just look at the other videos, and you can find some videos interesting, so you can just look through them. And there are the videos available on this channel regarding the JEE Mains and the JEE Advanced previous year questions, so you can also follow that. And if you liked this video, then you can share with your friends. All right, yeah, thank you.